You missed the first 5 minutes of the lecture. Why am I not connected?
This is
Oh, because there's no phone.
is flipped.
No, it's not flipped, it's a different camera. It's not this camera yet. Now it should.
Oh.
Well, we're so much used to our usual world. Now it's better. And now what happened? Why is it blurred? Okay. Hmm? No, that was
the camera.
I forgot to put the power in.
Okay.
Yeah. It's an example of if you're used to the mirror so much, the real life looks very weird. Okay. Last lecture. And oh, we had a Zoom. You guys should write to the Center for Technological Excellence that they need to put a camera.
Yeah.
I have written to them and they agreed. But once they came to know that they have this camera, they said, no, you already have a camera, then you don't need. So they approved it and then
Is it?
after 4 emails,
How they got to know that you have this camera?
because they,
You are here.
so during COVID, there was all this activity about online learning. So that is how this camera started. So after a year, so I wrote to them that students are finding this very useful. So put a camera in here, and that's an expensive affair. And I said better than this camera and all that. And I gave them examples of our videos, saying that see, this is very beneficial. Students are enjoying it, and they were also very excited about it. They said, yeah, this is one of the good videos we have seen. They were very happy about it. They said, yeah, sure, let's do this. And about 3 or 4 emails down the line, they said, so how did you take those videos? I said, hey, we have a camera, my department gave me a camera. They said, oh, then we cannot fund you because you already have a camera. We can only, no, currently we are not upgrading equipment. We are only if you want a fresh one, then we have budget for it. Our budget doesn't allow for upgrading, so I lost it. It was almost like we had. It was frustrating. Sometimes you don't want to talk too much. Once it's approved, just keep quiet.
Yeah.
Up and down. Oh, it's too sensitive to do.
You better explain. It is one to again. Let's go this side.
Sensitive when it reaches in the front. But this. So I need more time. So all homeworks are due tomorrow? In principle, like you can submit it. Most of you have submitted, not all homeworks, not the exam part. Why is Pooja so surprised? Homework 12 is not submitted yet. I have not even taught it.
I thought homework when you some.
No, so, okay. I think homework 11, all of you guys submitted, so. And I also graded, and by grading, I mean I just wrote. I really graded seriously. So homework 12 is the only remaining. It is officially due tomorrow, which is not fast. Let's,
This video, video.
and what?
Videos are 2.5 hours in each.
That's a resource. Right? It's not how to work, yeah, good point. Try to do it using whatever we are doing today, it should be possible. Like, if you,
And then if you ever need to, if you get stuck, you can work it.
and, yes, but I agree that compressing this much of content in just 2 weeks is not the best thing to do.
Extremely tight.
Yeah, it's probably goes again, it's not going to be very useful. But I didn't have any. Either I skipped the whole thing, which also didn't think. So the idea is that if you just, another, like again, from the perspective of the instructor, I think that, okay, if I ask them to do it, they will at least be aware of what is going on. Probably you won't understand the content, but at least you get a feel for what this is all about. And hopefully next time somewhere else you will get a better opportunity to study. Okay. So, okay. So final exam. Mine. Let's see. Questions? You guys keep mumbling the moment I turn around. What is it you guys want to ask?
We are talking about the reminder,
Reminder, what is a reminder?
this one.
What reminder? I forgot.
No, this one is just, I say reminder, have I exam reminder.
Yeah, this is exam reminder.
Yeah, we just.
But what's the joke?
Nothing.
Okay, I don't understand the jokes either. Okay, there is,
We see the meanings of that reminder, right? You understand that
meme, I don't even know what meme means, I think I've read
memes
memes, yeah, I roughly know, yeah, but I never.
is like, yeah, those one means, and then they just give this one is a reminder for you, something like that.
So what is the joke when I write final exam?
No, that one is a reminder, you have to, you cannot forget that.
Oh, yes, yeah, you don't want to forget the final exam, yeah, but it's 2:45, you won't sleep that long.
Our quantum is 5 to 7 p.m. Yeah.
Oh, quantum is 5 to 7, yeah, oh, evening, right?
Evening, yeah.
So you cannot forget that. I have forgot, like, I was in a high school where things are very serious. And I slept off, so I didn't show up, so it's not pleasant, that experience, yeah. But I have a few things, right? I mean, there are 2 questions, right? 4 questions is, no, 3 questions, right? 3 questions is bring home, bring from, bring home, let's say.
I think take home also.
Take home is okay, I think.
Because homework is homework, but we bring it. Take home, take home, but bring it.
That's true. Okay, come up with a quiz, come up with a better word.
What do you submit the quiz?
Oh, how do we submit a quiz? Yeah, no more quizzes. I don't want to grade. Okay. Yeah, yeah, today you can submit, but after this, no quizzes. Next semester, yeah. Are the quizzes useful? Do you guys enjoy quizzes or is it a chore?
I enjoy it.
Huh? You don't like it? So.
In high school, we used to, chemistry / physics, science teacher, he always did these do nows.
Do what?
Do nows.
Do nouns.
It's just he writes on the board, do now.
Oh, do now, I see.
Kind of thing.
It's almost something. We read that.
We do
Oh,
the
so
first
that's-
thing and then-
Oh, yes.
Same quiz.
I tried to read about this. I don't have a good answer for. Yeah, so what's the difference between winter solstice and perihelion? I'm confused. Like whatever we are talking about is the perihelion, which is I think the January 3rd,
Yeah,
but
gosh, that's.
how bothering.
Orbit. the
Yeah.
planetary Orbit, that's it. Winter solstice deals with the tilt of the plane.
Of the axis, yeah. So-
Perihelion is when, like, the Earth as a whole, like, when is the Earth is closest to the sun. But
Yeah.
the solstice is when the southern hemisphere is more like closer to the sun. That's what they say in the
Yeah, I spent a good amount of time and I'm not satisfied with what they explain, yeah. So, yeah, so certain questions can be open, right? You guys, kind of in your life, somewhere else, you will, maybe you can write a paper on it. Okay, 3 questions plus 2 questions. I have to tell you, I've at least made up my mind on 4 topics, right? One is functional derivative, which probably is a good thing to expect. I think I expect that you should have learned this. We have done a lot of examples. We've spent a lot of time. One of the simpler ones, not a too much elaborate ones, simple functional derivative one. But still, I would promise that I'll have Lagrangian, Hamiltonian, simple problems, okay? And I extended this to special relativity. And proper acceleration, that's what we will do today.
In equation, those 4 topics gonna come. Oh.
No, I will ask 2, I'll,
You select 2.
yeah, it will be hard for me to ask a question which has a Hamiltonian and proper acceleration, because that will be too advanced, yeah. So it will, probably I can connect functional and I won't try to connect, how about that? These are the 4 topics, simple versions of it. By that I mean functional integral, simple integral. I'll just create a functional integral, you have to evaluate it. Like we do in calculus, given an integral, you do an integral, right? Just do that, right? Second is, given a Lagrangian, write down equations of motion, or given a configuration, write the Lagrangian and find the equations of motion. Like last time I gave you that there is a mass sliding down an incline, write the Lagrangian for it. Those kind of problems, something simple like if a ball is falling, what is the Lagrangian for it? We always write Newton's laws of motion for it, write the Lagrangian for it. So those kind of simple, very simple situations. Classic situations like spring, a mass sliding down an incline. Go back to your university physics course and think about all the simplest configurations you analyzed there. too many masses probably is too complicated. Do the same for the Hamiltonian, like the Hamiltonian for the same configuration. Simplest, maybe 5 simple configurations. And proper acceleration. By proper acceleration, that's what we'll do today. Like when we do, when we are studying physics, introductory level physics for the first time, when we study, we first define velocity, then we define acceleration, then we define mass times acceleration is equal to force. So force and mass comes into picture. But first is velocity and acceleration. And even before we do forces, we talk about kinematics. How does a uniform velocity trajectory looks like? That's a straight line, right? A uniform acceleration trajectory is
It's just a horizontal. Uniform.
uniform acceleration, constant acceleration. What is a trajectory? Oh, I shouldn't say trajectory. What is the equation for the path with respect to time? What is the curve that
Oh.
it's parallel? Now we are doing relativity. Things change, right? How will a uniform velocity look like? And how will a uniform acceleration look like? First of all, what does it mean to say what is uniform acceleration? Like uniform acceleration meaning itself, is it something that is frame independent? If I'm in one frame, I measure the acceleration of the system. I change the frame, the acceleration changes. So what does it mean to say that uniform acceleration? We know that velocity is not an absolute concept, like it is relative, right? So does it even mean anything to say that acceleration that is uniform? So we will see that yes, there is a concept associated with acceleration, which is very useful and which will be called the proper acceleration. If something is going with proper acceleration, what is its curve? The answer will be hyperbola, but we will try to do that. Okay. So, so we have law. So this is relativistic kinematics. That's what we want to do today. And I have 50 minutes. So we have Lorentz transformation. Implies, what it implies is that there exists, I think, we said this, right? That c square, p square minus z square stays fixed. Right? Is this quantity, which is, this is the time coordinate, z position coordinate, the difference between these quantities remain fixed. Constant in what sense? Constant is usually with respect to something, right? It's constant in what sense?
Constant in.
No, it's not in time. Like energy, that's a conservation principle. When we say that something is constant in time, then we say something is conserved. But this is constant with respect to what? Okay. Yeah, good.
In the reference.
Reference frame, right? It is like whether I'm measuring this quantity in standing here, or I measure it while I'm in a car moving, this measurement will be the same. Which means that that is something you want to compare. Often we say length contraction leads to paradoxes. Time dilation leads to, you won't match. If Pradeep measures a quantity, the Lakshya measures a time, you compare it, you disagree, and then you have arguments. Instead, what relativity says is that don't compare time. What you should compare is this quantity. And then you will match. Then it doesn't matter who was moving. right? It is equivalent to saying that, let us say, there is a world in which we don't perceive people the way we are perceiving here. We only perceive shadows. Imagine a world, you have to imagine it because we can see each other. But imagine a world where you're seeing only shadows. There is the stories where you're in a cave and there is light coming from the backside and you only see the shadows of the world around you. So if you're seeing a shadow, how it will look like is this is a vector now, right? The physical quantity is vector, but the shadow of that is a component, right? This is AX. Now, X component of it in different rotated frames will be different. What will be the same is the quantity AX square plus AY square. If people were to compare the components of a vector and I said that, oh, I measure the X component of a vector. In a rotated frame, Ryan measures the X component of the same vector. We won't match. That doesn't mean that either of our experiments is superior or inferior. It's just that we are we are trying to compare something which shouldn't be to begin with matched at all. Right? We should have started with matching something much more fundamental. In that sense, if relativity is true, and if we allow labs to be moving with respect to each other, one is doing a measurement in moon, one is doing a measurement in earth, both of us, if we are to match, then we have to look for quantities like this. This is one quantity that's the same. So this will be often called an invariant, Lorentz invariant. So this is a Lorentz invariant object. Right. This quantity here, the length of a vector, is a rotation invariant quantity. Under rotations, it remains the same. It is constant under rotations. Constant with time, constant with rotation, constant under Lorentz transformation, which is what you meant by frame independent. Okay. If this is the same, differences are also the same. So it is also correct to say the small differences in this. And we will say minus plus b squared. And maybe I should also point out why stick to one dimension, at least for some time. So vectors. But most of our discussion will be one dimension, we'll be keeping only one dimension. This remains the same, and whatever that quantity is, we will define it as minus ds squared. So that's just a definition we are making. Now ds is special in the sense that it's a Lorentz invariant. If I were to measure the difference between two quantities, which is having a one time and three space quantities, this quantity is Lorentz invariant. Anyone measures it, they will match. No discrepancy between them. So that's a good quantitative method. We will define a 4 vector. 4 vector will be like a 3 vector. Let's say A mu. So that's an index now. So A1, A2, A3, A4. And this will have, that's the time component. And that's the spatial component. This is 1, 2, 3. Okay. If there is a vector, we have a magnitude of a vector, and a 4 vector has a magnitude. So this is A mu. A mu will be defined as minus A0 square plus A dotted with A. That's just a definition of a 4th vector. You add a 4th component to it, which is a time. If it is a position, it is a time. But any vector could have a 4th vector. So everything that you studied in introductory level physics, you have to start thinking of it as a 4 quantity. Okay, so examples are, this is good too because it's a one lecture special relativity. We'll try to put in as much information as possible. Time has a fourth component, which is, sorry, position has a fourth component, which is time. And that's C, to make it dimensionally correct, you make it C, so position and time. Next is velocity. What is the, oh, move it. Maybe it is the opposite. That is all on trying to finish the course in 50 minutes. Okay, no, I don't have 50, it's okay. So there's a V. What's the fourth component of velocity? Anyone?
Isn't that still time?
No, it won't be time. It turns out it is C, speed of light. Okay, and just to make it all okay, there has to be gamma also. Okay.
Isn't there also a gamma in the position one field?
No, this one is pure position and time. This is a 4 vector. To make this a 4 vector, we'll see this in a few minutes. I'm just summarizing this. This is the nice part. Momentum is, what's the fourth component of momentum? Very good, right? So it's energy. And just to make it dimensionally correct, so it is A over C. Okay. And what else can, so one should talk about acceleration. Okay. Acceleration is not clean, maybe. We will talk about it, right? It's not a clean object that and force. Force is equal to force is time derivative of momentum, right? So
Be the power, the time derivative of. the-
power, very good, yeah, power, right? So let's say power. Okay, dE by dt. And one can ask, what about electric field? That's where things get really interesting. Remember, electrodynamics is where relativity came, right? Electric field is not a vector at all. In Lorentz case, it's a tensor. So electric field will be Ex, Ey, Ez, 0, Bz, By, X, 0, 0. That's a tensor. Minus X. That's an antisymmetry, and probably in electrodynamics, if you have seen it, you might have seen this in some form. And notice why this is important is if you measure velocity in one frame, it won't match with another frame. If you measure position, it won't match. What will match is the difference between the square of the difference between them. So if you measure velocity square, subtract it from c square, it will match, and there's the gamma also. Okay, it will match. Momentum, if you measure in 2 different frames, it won't match. But momentum and energy together, if you measure and subtract it out, squared quantity, they will match. Okay, is that clear? So that's how relativity works. So you always want to find invariant quantities. That is a key point in relativity. Don't talk about other quantities. Like when we talk about light contraction, It is glamorous, it is very interesting, but that's not the idea. We don't want to worry about length quantification. We want to talk about invariant quantity. Eventually, though, you have to talk about length, eventually you have to measure distances, and that's where the interpretation challenges comes in. It's not that we don't worry about it at all, but the main theme is that the invariant quantities are here. Okay, so we want to build this invariant quantities. And we already talked about there is a ds, so that will be called ds will be called the proper time. Proper time because there is a position and a time, each of which doesn't match in different frames. But this is a special quantity, which we will call it the proper time. Every event, if you were to square this and subtract it, there is a definition called proper time, which will match. So ds square can be written as minus c square dt square 1 minus 1 over c square dx by dt dotted with dx by dt. If we are talking about the velocity of if this position and time are associated with the trajectory of a particle, that's a velocity that shows up, and the negative sign can go away. And we have ds is equal to c times dt times 1 minus v square over c square. So that's why it's called proper time, in the sense it is related to time. T and proper time. This is a gamma that can be written. So gamma is equal to c dt over ds. So you want to think of it like this. Proper time is related to a difference in time and the gamma factor. But we will use this as a user level. The second equation will play an important role in the algebra that we do. Okay. For position. Remember, in introductory level physics, first thing we do is introduce time. Oh, what happened? Okay, okay, yeah. So, time and position, we introduce time and then we introduce position, right? Here, both come together, C and time and position comes together. So for position, have both time and position, that's C, T, and X. Yes, so that's for position. For velocity, once you have position and time, you define velocity. Now it's for velocity. Remember, velocity remains the same. Nothing in relativity, we don't change the definition of velocity. It is only how it transforms the change, how we combine things that change. Velocity is velocity dx by dt, the normal derivative with time. What we are going to change is introduce new things so that we can identify some invariant quantity. For velocity, we will say this is the definition. V mu is going to be derivative of dx mu. But I want to take the derivative not with time, because time is different in different frames. This is a nice quantity. So I'll take the derivative with ds. This is not the normal velocity, this is for velocity, an abstract concept. Don't confuse that this is more fundamental. It's just a definition here. You want to keep your velocity as the old velocity. For all purposes, velocity is velocity. Okay? V mu is it, but where is the velocity sitting here? First of all, we should say that, oh, that doesn't make sense. Dimensionally, this is not correct, right? Because this is position, that's also position in the sense c times t. So it's better to multiply by c. So you just multiply by c, those are the definition of the dimension of velocity. So what is this quantity equal to? V mu. Oh, did I move out? Remind me, please. I'm not good state of mind today because I have 35 minutes.
You can extend few minutes, we can extend few minutes.
Yeah, but I need a lot more. If you can imagine teaching special relativity in half an hour is not that easy. Okay, but I'm gonna attempt. Okay, so the mu is taking the derivative with time is taking time a derivative here, right? So we do. There is already a c there. And then there is c dt over ds and dx over ds. Okay. Use a chain rule in the second part. First of all, the first one is gamma, right? That is at gamma here, right? So it is c times gamma. And second one, introduce a dt there. Use chain rule. That way I have velocity now. I want to connect with velocity, the old velocity, right? So that's velocity. So this is equal to c times gamma. And c times dt over ds is again gamma. So velocity times gamma. Right? And that is what I wrote earlier, that this is c times v times gamma, if you want. Notice we have not done anything new. What we are finding out is that what is this fourth piece which I should measure so that together that is an invariant quantity. What is the time component of velocity that I should measure so that when I take the square of space and square of the time component, together it should be invariant. Velocity remains velocity. It's just I'm searching for a fourth component. So what is this fourth component? Let us see. Go here. So what is the magnitude? What is the quantity that remains the same? What do you expect this would be? Huh? Oh yeah. 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 So let's calculate the invariant quantity associated with V mu, right? So V mu, this means the length of the squared quantity, the length of a vector if you want, but it's the length of a fourth vector that will be equal to V0 square minus V dotted with V. Agreed? Right, that's the definition of a four vector.
Minus should be.
Oh, sorry, minus should be. Good. I should also point out different textbooks use different notations. I will try to consistently, or I always use space as positive and time as negative. Almost equally distributed, half of the textbooks will do opposite, and generally it is the high energy people do this as negative. Whatever I'm doing is more like general relative. That's again, there is no such rule, but most of them tend to be level. So be careful with which textbook you use. What's the time component? It is c times gamma. So it is minus c square times gamma squared plus v square here and gamma square. That's equal to minus c square gamma square 1 minus v square over c square. And what is that equal to? 1 minus beta square times gamma square? 1, right? Last time we saw it, that's minus c square. It is good. So speed of light is invariant, right? That is in Lorentz transformation, that's immediately there. So what should you measure whenever you want to measure light, speed, you should measure the speed of light. It is not very physically useful because speed of light is anyway constant. So, but it is consistent with our idea that whenever you're having a physical quantity, find an invariant quantity. In the case of velocity, it turns out to be the speed of light itself. Like remember again, this comes out very dramatic in magnetic field, right? What is the idea of a magnetic field? If there is a charged particle moving, right, it will create a magnetic field. Correct? Agreed? That is the idea. Like there should be a current, but even a charged particle, moving charged particle will create a magnetic field. I am in a car, I adjust my speed of the car so that I have my speed of the car exactly that of the charge. What is the magnetic field I will measure in the car? Of the moving charge? Zero, right? Because velocity is zero for that car. So magnetic field has disappeared. Right? So magnetic field is relative. Right? So same thing with electric field. So all that we studied is practically useless because you cannot compare them. What you can match is, this is just for your information, that E square minus C square B square. If you were to measure this, remains the same in every frame. So it's useless to talk about magnetic field. It's useless to talk about electric field. You should talk about the difference in those quantities, squared differences. Only then it will match at very high relativistic speeds, which is very common in atomic physics. And you do talk about this. So that's what we're trying to build. Like we're trying to identify these kind of invariants. Like what remains invariant. So velocity has this, so that's consistent. Now we go into for momentum. Or we have V mu, right? So great, yeah. So this is what this is like all this is relatively straightforward until now. This next step is what where Einstein's intuition came. So V mu is C times gamma and V times gamma. That's gamma. Okay, don't confuse with V. That's the same thing. I'm just rewriting this idea. If I multiply with mass, V mu is equal to MC gamma and MV. This we will say is for momentum. Oh, we should move. For momentum, it's going to be P mu is equal to MC gamma and MV gamma. Einstein changed, so this is where the change happened. Until now, there is no change, right? It's just combination of parameters that are done. Here is where Einstein changed a physical quantity. He said, this is energy. And that's momentum. So he changed the definition of momentum. Momentum is no more mass times velocity. It is mass times velocity times gamma. So momentum in relativity is not mass times velocity. It is mass times velocity times the Lorentz factor, which is mass times velocity over 1 minus v squared over c squared. So that's the chain. That's a and energy, similarly, mostly kinetic energy, but now kinetic energy is a misleading term because kinetic means movement, right? The way we interpret kinetic energy in introductory level physics is that energy associated with movement. But here, there is an energy associated with rest also, which is mass. Just because you have mass, there is an energy. So it is not kinetic, it is kinetic plus rest mass. Okay, still there is no potential energy in here. There is a potential energy will come in. But this is kinetic, but not purely kinetic, kinetic plus rest mass. Okay, so this is mc square times gamma, so there's a c there, and that's the same as mc square over 1 minus v square over c square. Okay. Velocity had invariant quantity associated with that c. What will be the invariant quantity associated with momentum and energy? Momentum is nothing but mass multiplied with v mu. So you multiply mass square there. That's mc square, right? So if you square this out, so this is e square over c square minus plus p dotted with p. That's the squared quantity of this. That is nothing but this quantity multiplied by m square. That's equal to minus m square c square. And that's the famous E is equal to mc square. It's a generalization in the sense that if you were not moving, if velocity is 0, then this is equal to 0, then E is equal to mc square. And it is also popularized in the sense that we often we like to say this as energy is equal to this quantity, but in most of what we most of the current literature doesn't discuss this, but earlier relativity, it was common to talk about mass changing with velocity. You can say that mass effective is equal to m times gamma, right? And then you will see that energy is equal to m effective times c square. So when you see the equation E is equal to mc square, that's what they mean. Mass is changing with velocity. But that is usually not like, at least in the current literature, that's not common. In the early days of relativity, that was common. There was this Einstein himself entertained this idea a lot that maybe mass is changing. But these days, our idea is that mass does not change with velocity at all. It is the energy that is changing with the velocity. So we won't discuss this at all, but whenever you say E is equal to mc square, there are two ways of looking at it. Either it is in the rest frame and t is equal to 0, or it is interpreted in this. Okay, either way. Okay, good. Comments? Okay, so. Good. Okay. Little moment. Once we have velocity, next is acceleration, correct? So for acceleration, and we have a procedure at this point to proceed, right? If you have a 4 vector, take the derivative with the proper time, you get the next 4 vector. So for acceleration should be defined as a mu will be equal to d v mu over ds, and put in a c. That's equal to c times dt over ds times the mu over dt, right? That's gamma. That's gamma times the mu over dt, which is the same as, so multiply by gamma and take the derivative of the 4 velocity. That is nothing but d by dt of c times gamma and d by dt of velocity times gamma. So as you see now, acceleration is a little more tedious to do, but not that bad. So dt. This is our standard acceleration. Having no reference to forward acceleration, that's our the real acceleration, which changes from one frame to the other. So that's acceleration times gamma plus velocity times d gamma dt. Right, just taking the derivative. All this leads to the idea that what is this gamma? Let's calculate that. Go back to, we have an identity there, right? That v mu is equal to minus c squared. That's our velocity invariance. Take the derivative here with respect to, let's say, proper ds. So this will be v mu times should be down. It's not that crucial. A mu is equal to 0, right? Because that's doesn't with the derivative of proper time is 0. But we know a mu, we know v mu. Put them together, we get an equation there. So this is a mu. V mu is here, right? When I take the dot product, I have to put in the negative sign. That is the only thing that happens. So this is equal to minus of, there's a gamma here, there's a gamma there. So that's gamma squared c d gamma by dt plus the gamma there, so that's gamma squared times v dotted with a gamma plus v dt. Should be gamma squared c squared. Gamma squared c squared. Which one here? There is a c here, there's a c there, c squared. Right. C squared and dt. So there's a speed and an acceleration, speed and an acceleration. Speed and yes, dimensional equal. Okay. And that should be equal to 0. Okay. So that gives me maybe I can get rid of a velocity, right? Let's see. Let's take this d gamma by so slow. I'm still in the screen. Square. No, now you yeah. Gamma square, c square. Let's do this quickly. So that's plus gamma cube v dotted with a, and the next one is plus gamma square v square gamma by dt is equal to 0. Let me divide out by c square everywhere. So that's c square, that's c, that's c, that's c square. Right, so that way I have this cancels out, so I have 1 minus beta square showing up, right? So it is minus gamma square 1 minus beta square times d gamma by dt plus gamma cube v dotted with a over c square is equal to 0. Gamma square times 1 minus beta square is 1. So we learned that d gamma by dt is equal to gamma cube times v dotted with a over c square. All this so that I can replace this quantity here. This was a way to, a trick to calculate that derivative of gamma where can be put up explicitly. done that. 2. Okay. Okay. Put this back in there, so I have an expression for acceleration, and that is gamma times c, and now this is, I will substitute this also, so it is gamma 4 times beta divided with acceleration. I cancel one of the speed, one of the v over c, I wrote as beta. And the other one is gamma square times a plus that is a gamma cube, gamma 4 again, and beta divided with acceleration. Correct me if I'm missing something. That's what it is. Okay, that's your 4 acceleration. Okay, so remember, acceleration is everywhere here, right? There's acceleration here, velocity there. So it's not a clean object like we had a velocity object there. But if you want to compare acceleration, if 2 of us among in this class decide to measure acceleration, one in their own fast car and one in their slow, let's say in your rest frame in your lab, then this is the quantity you want to measure. One component here, one component here, then the square of these quantities, if you subtract, that will match. Okay. This comes out to be a space-like quantity. Notice this is a time-like quantity, right? It's a negative quantity, that means it's time-like. Acceleration comes out to be space-like. That's just for your information. One can verify that. That is actually a positive quantity, but here I'm not going to do that. If it is a space-like quantity, let's go to a frame. So mu will be equal to a0 square plus a divided with a. This is fixed, right? In every frame, this will be the same. Okay, so let's call that alpha square. Alpha is called the proper acceleration. Okay. But now, out of all those frames in which I can measure this, there exists one frame where this will be 0. So this is the redistribution of these quantities. Whenever you move around, what you're doing is that you're redistributing it. It's like saying proper length, proper time. If there is a frame in which there is no time component to a length, so it is proper time, proper length. So similarly, since this is a space-like quantity, there exists a frame. There exists a frame where alpha square is equal to a frame, right? There exists a frame. Like there exists a frame where alpha square.
For previous line, beta, you consider v over c square or?
Other one?
For previous line, beta, you considered
V over C.
v over c.
Yeah, it is not matching
So from here, there are no c, right?
from here.
Yeah. So here is a c and the other side, this is v.
There was a C, right? And d gamma by dt is gamma cube V over C dotted by A over C. C cancels out, that's beta.
Beta, and for other one, that a,
This one,
the,
this one.
yeah.
Oh,
There's another
so,
V.
so
Whatever v.
that doesn't match. Okay, let's see, V times gamma cube V dot over C dotted with A over C. Oh, I'm missing something. Oh, that's right. This is a vector, right? It's not a vector, right? Yeah, you're correct. So this is gamma raised to 4. I want to move a c here, then that's beta. And then that is beta dotted with a. It's correct because this is a vector, that's a scalar, must be wrong, right? So then the beta. And otherwise it's a scalar. Thank you. Thank you. Okay. Okay. Sorry about that. Clear? Okay, very sorry. Yeah. But I was saying, from that point on, there exists an invariant quantity, which is the proper acceleration. That means that there exists a frame in which the time piece is 0. There will always exist a frame in which this will be 0. Okay? It is like saying that if you were to plot acceleration, this is the magnitude of acceleration, and a 0, this will be a hyperbola, right? Because that's a constant. And if you want a to be, this is a space-like quantity. So this will be like this space-like quantity. And we are talking about this frame. Remember, moving along this line is changing frames. So that if you're right on that frame, there this a0 is 0. So that's a special frame, it will always exist. In that frame, you have acceleration because that beta will be 0, so this will be equal to gamma square times a, and gamma is also 1. So that is acceleration square. There exists a frame in which alpha is your current acceleration. But it's just one frame. If you're moving, you're accelerating, so your velocity is not going to stay the same. So the moment you change, you have to jump onto the next frame. Right? If you want to have the interpretation of the proper acceleration, because velocity is changing. So as you're moving, you have to keep changing your frame if you want to have the interpretation of proper acceleration. Proper acceleration is not an invariant object for all frames. So you have to go from one frame to the other because your velocity is keeping on changing. It's the acceleration in your rest frame. So sit on the particle and measure your acceleration in a sense. Right? But then you would say that if you're sitting on the particle, then how do you measure the acceleration? So that's what you want to capture, make sure you grasp.
So if invariant in the frame,
No, not in the frame. This quantity will be the same for all frames, right? That's okay. But then you say that how is this connected to the acceleration? Like you usually are accelerating, like I'm measuring, like I throw a ball up, it is accelerating. How is that related to the proper acceleration? So you say that you sit on the ball and instantaneously you measure the acceleration. You're at rest at that time. At that time, whatever you measure, that's your proper acceleration. That's exactly equal to the proper acceleration. But the very instant, because you're accelerating, you will change your velocity. And that will change the
that means acceleration is not invariant. Because the velocity for velocity was invariant, right? Because it is
no, for acceleration is going to be the same. Because this quantity is the same, left hand side.
or you mean like
But if you want to, you have to keep jumping the frames further. Because you're keeping on moving. There you have the luxury that there exists a frame which is going to be the same all through. Here you have to be with the particle, you have to keep catching up with the particle. So that's the idea of a tangent.
so
frame.
what is the difference between for acceleration and for velocity in terms of like frames?
In for velocity, you can stick to one frame.
Yeah.
And you're good. It will be always your favorite frame. But if you want to have your acceleration match with the proper acceleration, then you have to keep jumping on the frame, which is understandable. As you're accelerating, if you're at rest, then you have to keep jumping on the frame because velocity is keeping on changing, right? In the lap frame.
Oh.
correct?
Yeah.
So. And that is a common concept you will see. You will always talk about a rest frame. In relativity, you will see there's always the idea of a rest frame. All the measurements will be done in the rest frame. Okay. Okay, so. So now we have the idea of proper acceleration, then we have to talk about what's the motion, how does this motion look like in a proper acceleration? Right, that will be the in normal physics, we say uniform acceleration, integrate out, we get velocity, do the second integration, we get position as a function of time, how does it look like? And it turns out to be a parabola in introductory level physics or Newtonian physics. Here it is going to be a hyperbola. So let's do that. So, so motion. Move the camera, right? Motion under. Still in the frame. Okay, good. So, I'm in the frame. Yeah, works well. Okay. Motion under proper acceleration.
Jumping to the next one.
Jump in the next one, yeah. What's up? Yeah. Okay. Remember, this is like, if you are in the proper frame, right? I go into this frame, right? And then I have to interpret this quantity in here, right? So that's my acceleration if you want. This quantity has to remain the same. So proper acceleration amounts to d by dt of velocity times gamma is a constant. Call it alpha. If something is a constant, we would say V times gamma is equal V final, right? V minus V initial, right? V initial. And let's make it one dimension. 1D motion. So I remove the vector sign. So V initial times gamma is equal to alpha times t. Right? Let's also set the initial velocity, it's 0. So I'm dropping a ball and it is falling off. So this goes to 0. So initial time at time t is equal to 0, V initial is at time t equal to 0, velocity is 0, so V initial. So this goes. So I have velocity. So V times gamma is equal to alpha times t. That's our equation. Gamma, remember, is 1 minus V square over C square. Right? We'll explicitly write that. 1 minus V square over C square. Square this quantity so that I can get velocity because I'm interested. So I did one integration. So now I'm velocity. I do second integration, I get the position.
So does this initial condition, we make the.
It's the choice. I
Go
think.
at t equals 0. How do we consider it?
Like when I'm saying when we drop a ball, right? In uniform acceleration, I have the choice to either throw the ball or at t equal to 0, drop the ball. So this is a configuration dependent. Like any differential equation has two initial conditions. This is one of the initial conditions I have to provide. If you change that, things change. Like then we have to reanalyze that, but it should be straightforward, won't be too complicated. This is V square over C square. That's alpha square, T square. solve for velocity and what is it? So divide by c square maybe everywhere. Right, so this is v square over c square is equal to alpha square over c square. Make it alpha over c raised to 4 and c square t square. And minus of v square over c square alpha square over c raised to 4 and c square t square, like dimensional. So that's the same as v square over c square is equal to alpha square over c raised to 4 c square t square divided by 1 plus. Probably that's the way, right? Take the square root. So v over c and I can move. Oh, time is up. I'll take 10 minutes. You guys promised me you can, Pradeep promised me that you can take extra time.
Okay.
Okay. But we'll finish quick, okay? So this is v over c is equal to, take the square root on the right hand side. So that's alpha over c square. Then there is c times t. Probably I want to get rid of all the c's. Let's get rid of all this extra c's. It's just 1 plus alpha square t square. No, still,
So
it should be c raised to 4.
four.
Am I good now?
I think. T square in top. C square, T square, C square, cancel the T square is T square. This T,
So it's t there, right?
yeah, that's T square.
Oh no, I took a square.
Okay.
I think that's okay.
No,
Please, C. And yeah, okay, so dv by dt then, or dx by dt then is equal to, I cancel out all the c's. So it is alpha t over 1 plus alpha square t square over c square, right? So this is an acceleration times time is velocity, so the dimension is right. That's okay. We can integrate this. In the strings. Okay. So dx is alpha t. Like the same, if you remember introductory level physics at the early stages, we integrate velocity to get position. So we are just doing that. Oh, okay. So substitute 1 plus alpha square over c square t square is equal to u, right? And 2 times alpha square over c square t dt is equal to du, right? So t dt is du. So t dt is equal to c square over 2 alpha square times du. So there's an alpha there. That's what it is. So this is equal to c square over 2 alpha du over square root of u. So u raised to, so c square over alpha u raised to minus half plus half, and then there is a half. There is a half. but the half cancels that too. So that's equal to c square over alpha times square root of u. But square root of u is 1 plus alpha square over c square t square. And the left hand side is x. Square this out. So you have x squared times alpha square over c raised to 4 is equal to 1 plus alpha square over c square t square. And there is a constant also that shows up now, right? So this could be an x minus x naught or x minus x naught, let's say. Well, and we want to put this together in such a way that alpha square shows up here. So that's x minus x naught the whole square. Here I want minus of c square t square is equal to the distance. So I think it is c raised to 4 over alpha square. So alpha has a speed, 2 speeds. I think that's 2 distance remaining. And that's an equation of a hyperbola. Right? And where the acceleration is now showing up in the denominator. Right? So, and in your homework, you will see that how this, so for small speed, so for v very much less than 1, what should this equation become? Parabola, right? This is a hyperbola. For this same equation will become a parabola. X minus x naught will be half alpha t squared. And that you do in your homework. I can try to do this as a plot. So how this comes out is that, so this is your, remember, we plot c times t and z here, right? Or x in this case, right? Now, this equation here, it's like this. That's your path of a particle, like the particle is going along a hyperbola. If you were in the non-relativistic regime, it is pretty much the same, but then this is a parallel. And you can see that somewhere along at this point, for example, that's your tangent, right? You start going faster than speed of light. If a stone in uniform gravity, if there was no surface here, it kept going with uniform acceleration. Very quickly, it will go faster than speed of light. Like if you ever calculate in a capacitor, how much time, like what is the acceleration or what is the velocity of an electron inside in an electric field? If you're not careful with the numbers, very quickly you will be going faster than speed of light. So non-relativistic physics doesn't work, and that's because only in this very small time regime it actually is not relativistic. Very quickly it can become relativistic under uniform acceleration, but it can be corrected using this. Okay, so that's, sorry about the rushing and hurrying.